Hello and welcome back to Calculus 1 for one last time. This is the last lecture. Yes, we are going to talk about U substitution for integration. And in some sense, this is the most important technique of all techniques of integration. Now, where are the rest of the techniques if they're not in Chapter 5? They're in Chapter 7. So you are going to learn the most important now. Then you're going to take a break from integration techniques and do application of integrals in Chapter 6. And then in Chapter 7, go back and learn other methods of integration. Now, those other methods of integration, which is in Calc 2, will mainly refer to this one. So if you are taking Calc 2 anytime soon, make sure you know this section, otherwise you are doomed. Now, what is this all about? Well, who can tell me what is the most important and the most utilized technique for derivatives? Chain rule. So this particular integration technique is the one that would undo the chain rule. Yes. So if you are to write, say, the derivative of f of g of x is equal to f prime of g of x times g prime of x, then you can reverse this formula by shipping this dx to the other side, creating differential, or you can also integrate both sides like this, where this stuff would cancel each other, and you are creating the formula which states that the integral of f prime g of x dx times g prime of x dx is equal to f of g of x. We can do plus c, right? Now, it means very little when you write these formulas like this if you are not able to apply it. So we actually learn this and understand this through working out 5,000 examples. So what happens if you have to integrate 2x plus 5 dx? Well, hopefully you will integrate this term by term, and you will get x squared plus 5x plus c. Right? The derivative of x is x squared over 2, and then 2 cancel. And the integral of 5 is 5x. Now, as the next problem, we integrate 2x plus 5 squared dx. Well, you should know that you can actually FOIL this and get 4x squared plus 20x plus 25. And then if you integrate each one term-wise, you will get 4/3 x cubed plus 10x squared plus 25x plus c. So you can still work this out, right, if you have a square on top. But then you reach the problem of 2x plus 5 raised to exponent of, I don't know, 83. Good luck foiling, right? So it would take a very, very long time for you to FOIL something like this. So what do we do? The trick of this method of integration is to think in terms of, can I combine a lot of stuff on a pile and call it one variable and then integrate that instead? Because that will simplify things. You see, I can integrate x to the 83 easily. But to integrate 2x plus 5 to 83, I actually have to FOIL this until, right? Because over here we just have the square, and then we FOIL, and then we integrate, right? So now we are not going to apply 83rd power on this. So we need to be clever about it. Let me define variable u as 2x plus 5. Because I want to make the entire thing just be u to 83. Because I can integrate, right? If I have a single variable raised to 83, that's easy. I have the basic formula for that, right? But now this comes at a cost. Because what you are doing is you are transforming the integral that was in terms of x into integral that is in terms of u. So you are changing the domain. Domain used to be in terms of x, now it's in terms of u. This is transformation. So now, if you are transforming this x into u, well, then you have to also transform this x, because it's dx, and now your new integral has to be du. So where is the link? Well, differentiating your u equation here will give you du dx, which is 2. And this is where the transformation between dx and du happens. So now du is equal to 2 dx, and finally dx is equal to 1/2 du. So please understand that we replaced 2x with u. And now I am going to replace dx with 1/2 du. So the entire thing is called substitution because you are substituting u for x. Now it's actually the entire expression that you are getting rid of. And as I said, right, there's no free lunch. We also have to transform dx, and that will have, more calculations. So now we kick 1/2 outside, and all I have to integrate is u to 83 du, and that is the basic integral. So now that's 1/2 u to the 84 over 84 plus c, which is 1 over 168 u to 84 plus c. Now our answer is in terms of u. The problem is in terms of x. And that's not good. We have to have our answer in terms of x. So we go and we back substitute, right? So instead of u to 84, I will write what u is, and that is 2x plus 5 to 84, and then plus c. And that is the answer. So the answer is has to be in terms of the same variable as the original problem. Let's do another example of this. Say you have integral of square root of 3 minus 4x dx. What can you integrate easily? Square root of x. So you are seeking to make whatever is under the square root one variable. So u equals 3 minus 4x. Now you know that you will need the derivative to transform dx. So find du dx right away, which is negative 4. Write that du is equal to negative 4 dx. And then solve for dx, which is negative 1 over 4 du. So now when you put this thing together, you have a square root of u times negative 1/4 du. So what I have done is I replaced whatever is under the square root with u, because I defined my u that way, and then replace dx with what dx is, which is negative 1/4 du. So now I kick negative 1/4 in front of the integral. I write u to the 1/2 du, so it's easier to add 1. And then negative 1/4 u to the 3/2 divided by 3/2 plus c. The 3/2 becomes 2/3. That cancels, so this is now 1/6, right? So negative 1/6. U to the 3/2 plus c. Again, we cannot leave our answer in terms of u because the problem was posed in terms of x. So we have to go and substitute back our value. So that's negative 1/6, and instead of u I have to write 3 minus 4x raised to the 3/2 plus c, and that would be the answer. Now this is integration, and because it's integration, you should be able to take the derivative and get the problem you started from. If you don't, your answer is wrong. So let's check by taking the derivative of negative 1/6 3 minus 4x to the 3/2 plus c. We first observe that we have to use the chain rule, because this is the chain, the u sub is backwards chain rule, so it should be common sense that we are going to use the chain rule now. So now what we do is we copy the constant, which is 1/6, negative 1/6, take the derivative of this, so that's 3/2, 3 minus 4x to the 1/2, and then times the derivative of the inside is negative 4 as a chain rule. So now I have 6 cancels 3, we get 2, 2 times 2 is 4, so negative 1/4, so that all cancels, and there it is, square root of 3 minus 4x. We're good. Another example. Integral of basic e to the x dx is what? Yes. Right? But now, if I have integral of e to the 3x dx, I asked you to memorize the formula for this, but I also promised you that I will show you the actual works behind this. And no coffee. And we can deal with this by saying u equals 3x, because we know how to integrate when you have just a variable in the exponent. So now du is equal to 3 dx, from where dx is equal to 1/3 du. So integral e to the u times 1/3 du. See, entire integral now is in terms of u. We kick 1/3 outside, we get integral e to the u du, which is 1/3 e to the u plus c. And now we have to go back to x, You can just memorize the sentence. I don't care about I don't care about you, I care about the x. That's it. You will always remember that you have to go back to x. So we have 1/3 e, u is 3x plus c. Now I did ask you to memorize the formula for this, and the formula said integral e to the ax dx is e to the ax over a plus c. Well, you see that 3 from the exponent became just over 3, right? Which follows this formula. But you don't have to memorize the formula, because the same principle that we are learning now is applying everywhere, which is this kind of thing. So how about you try on your own to find the integral of, let's say, sine 2x dx. Technically you will be using the same stuff as the e problem. So try this one on your own. I promise you under the top of it's 2x. Because you know how to integrate signs. So as long as the computer doesn't push to you. No. So it's
yeah, we can find out that when we do all this stuff next to it.
9 a.m. classes are usually at 7 a.m. and then 11:30 classes are generally at 9. Yeah, so your stats class is at 9, right?
I got another exam in between, so.
Yeah. You have 3 on the same day before? 4? Nice. I never managed to pull that off.
If you have 3 on the same day, you can move that.
Yeah, you can move that. You have 2 in one day.
Yeah, I mean, I don't know about now since it's so late.
I'd rather just.
No, you probably still could.
No, you probably could. Especially at 4. Depending on your teacher.
Yeah, I never managed to put 4 on the same day. The most I managed is to put 3 in the same day.
What the hell happened to that story? Oh, I did 5 tests on one.
No, that story is that I had 5 tests on, which is worse. When people say you're mentally engaged, viewing exams over there, there's so much to do. All right. So we start again with the same. We say u equals 2x, du equals 2dx, dx is 1/2 du. What happened?
How many questions are on the final exam?
Enough, which is about 12 to 15. It's 2 hours then, so it should be fine. Yes, at least 5 questions. So we have sine, and instead of 2x we have u, and then instead of dx we have 1/2 du, which is 1/2 integral of sine u du, which is 1/2. What's the integral of sine? Very good. Plus c. So that's negative 1/2 cosine u plus c. Now we say, I don't care about u, I care about the x, which means we replace x back for u. 1/2 cosine 2x plus c. And that's the answer. So every single example which I did over here had a very basic and the easiest possible u substitution, because all of them, right, all of these guys had a linear u sub. But we can have problems like integral of x e to the x squared dx to work with. Now this is more involved. Look at this again. Do you see that your you have two functions? There is a function x and there is a function e to the x squared. Now you know how to integrate e to the x. So when you compare these two, it pretty much looks like that you need to make the exponent one thing. And that's generally what gives out what your u sub should be. So you look at the whole thing and you say, okay, what is complicated here that I can simplify and then integrate? And in this case, that would be e to the x squared. So u equals x squared. Because if you replace x squared with u, it will become e to the u, and that's easy. Well, let's deal with the fallout, right? If you do that, what happens with the rest of the stuff? So du is equal to 2x dx. And now this is the hard part to see. So if you really need to pay attention right here. Observe that x dx exists right there. So the only thing that you don't have is this 2. Well, you can ship that 2 to the other side. So that gives you that x dx is equal to 1/2 du. So now we can do our substitution. Instead of e to the x squared, I write e to the u. And instead of x dx, I am writing 1/2 du. So, you know, this type of witchcraft is not obvious immediately, but as you know, as you practice, it gets better. So one more time, I have a peanut over here. All right, in this peanut, I have this much, and all I need is that 2. Now there is an alternative way of dealing with this. When you have the peanut and you see that you have this much and you are missing a 2, you can also fix for that 2. You can say, okay, let me put 2 in. So now it matches 2x dx, but you have to put 1/2 in front to counter it, and that would be this 1/2 eventually. So there are 2 ways in which you can approach this, and I'll show the other way as well eventually. This is more streamlined when you know, compare what you have, and the peanut over here has x dx, which is this much. Oops, sorry, which is this much. So just ship 2 to the other side, and you get the substitution piece. It takes some time to get used to it. All right, so integral of e to the u is e to the u plus c. And then I don't care about u, I care about the x, which is 1/2 e to the x squared plus c. Nice. All right. Integral of sine to the 7x cosine x dx. So integral of sine to the 7x cosine x dx. Now this is where it starts getting tricky. The previous one was somewhat tricky, but this one is really getting there. In order to solve the problems when they become a little bit trickier, I generally ask students to look for what I call function derivative pair. So look for function derivative pair. Now that is obvious in the previous example with E. If you observe carefully, there is a function derivative pair. If you call x squared, if you call x squared a function, then its derivative is 2x. Don't worry about the 2, x is present. So you do have function derivative pair. So one more time, the very useful tool to figure out what's what here is to look at the entire problem and say, okay, I have 3 functions here. There is a function x, there is a function e to the x squared, and then there is a function x squared. So these are like 3 functions that all together I can write separately. What is the function derivative pair? Well, definitely nothing with e to the x, because the derivative of e to the x is another e to the x of some sort, and I don't have 2 of them, I only have 1. And then you also toss that off the list. You also know now that the derivative of x squared is 2x, and you know that you can fix the constant, so that would be function derivative pair. So now if I want to apply this approach to the problem above, what are the functions that I have? Well, I have just sine x, I also have sine to the 7x, and I have a cosine x. Do I have a function derivative pair? And the answer is yes. If sine is a function, its derivative is cosine. So it's very simple to kind of come up with this stuff. Now, here's the $1 million thing. This is u. So the function from function derivative pair is always your u, and its derivative will remain for du. Let's test this. So I said that derivative of sine is cosine So I will pick u to be sine x, which means that du is cosine x dx. That's awesome, because I already have cosine x dx over here as a string. That gets replaced by du. So the entire integral collapses to u to the 7 du. You're going from that trigonometric integral with the 7th exponent and all of the other stuff, right? Into u to the 7, which you can integrate in your sleep. So what happened? Sine is u, and cosine x dx is du. And you just plug them in, and you're done. So now you have to integrate. You get u to the 8 over 8 plus c, right? And then you have 1 over 8. U is sine, so sine to the 8 x plus c. If you don't believe me, go ahead, differentiate the answer. You must get sine to the 7x cosine x. Otherwise, we broke math. It's a lot of very interesting problems. Now the next one is also going to have trig, but it's different. Sure, we can check the answer. The derivative of 1 over 8 sine to the 8x is, we copy the constant 1 over 8. The derivative of sine to the 8 is 8 sine to the 7x, and then times the derivative of the inside, which is cosine x. 8 cancels 1 over 8, and you have sine to the 7 times cosine. What happened? Sorry? Nothing happened? Oh, you looked engaged in conversation about something that didn't happen. All right, fine. Anyway. Next. Integral of x to the 6 cosine x to the 7 dx. Do you get to pick a trig function now for you? Do you? We learned the method. Function derivative pair. What's a pair for cosine? What's a pair for cosine? Sine, yeah. Is there a sign there? Right? So we can't pick cosine. What makes more sense to pick? X to the 7. Because its derivative x to the 6 is present. So u equal x to the 7. Du equals 7x to the 6 dx. And you know what? I don't have 7x to the 6, but I can make it. I can just put 1 over 7 in front of the integral and 7 inside the integral, and now I have exactly what I need. So that's that other way of fixing coefficients. So now you copy 1 over 7 integral, and now here go with the peanut. See this? So in this peanut, you have your du, and outside of the peanut, you have cosine u. The entire integral collapses into cosine u du. Right? Because cosine x to the 7 is u. So that's just cosine u. And the peanut, as you can see, entire peanut is the string for du. And just plug everything in. And this integral simplifies into 1 over 7 integral cosine u. What's the integral of cosine u? What's the integral of cosine u? Sine. U plus c. And then I don't care about u, care about the x. 1 over 7 sine x to the 7 plus c. This is u sub. We'll do one more problem, and then we're going to take it to the next level. No. Integral of 3 over x ln squared x dx. Whew. That's a little bit excessive over there, right? But then if you employ the logic of function and its derivative, this problem is a joke. So do we have a function derivative pair in this problem? Do you see it? And if you see it, what is it? What happened?
1 over x natural log of x.
1 over x natural log of x. Now, what's the function? What's the derivative? That's what I'm looking for.
So natural log of x is 1 over x, but it's squared, but we do have 2 x's.
Yeah, we don't have to worry about squared. So what would be the function and what would be its derivative? What happened? What's the derivative of what? In this case.
Function is ln x.
There we go.
1 over x.
Very good. Because the derivative of ln x is 1 over x. That is the thing that you have to pick up. Here, I'll write it in blood. The derivative of ln x is 1 over x. That's what you have to pick up. Do you have 1 over x? Sure, it's right here. Do you have ln x? Sure, it's right here. Yeah, I know there's 3 and a square and all that stuff. You can ignore that. So, let's take a look at the solution. So function is the u. So u equals ln x. du is 1 over x dx. So what am I going to do? Well, first I'm going to kick 3 outside of the integral because it's a constant, and I can. Write 1 over x, and then ln x in parentheses everything squared dx. Now I really need you to stare at this so you can see it. These guys combined will make your du, right? And then you still have this, which is 1 over u squared. We defined ln to be u, so ln x squared is u squared. So the entire problem collapses onto integral of 1 over u squared du. So this whole thing is 3 times the integral of 1 over u squared du. This is 3 times the integral of u to the minus 2 du, which is 3 times u to the minus 1 over minus 1 plus c. That's negative 3 1 over u plus c, because u to the minus 1 goes in denominator. And finally, since u was ln x, you can just say 3 over ln x plus c. So now this is, you know, spicier realm. But again, the idea of figuring out function derivative pair really helps with figuring out what's what. The next task is interesting. Definite integrals. Right, Nancy? I don't want you to, you know, injure your spine twisting that way. So, we have now the definite integral from, let's say, 3 to 6 for now we can pick anything up. Let's just do e to the 4x dx. All right, so now we have a definite integral. And when you have a definite integral, your variable is variable x for the entire problem. So your limits are in terms of x. These limits are actually x1 equal to and x2 equals to. Remember where the definite integral is coming from. Computing area under the curve from point A to point B, so that you can write integral a to b and then f of x dx, right? So this a and b are both on x-axis, and that's why I call them over here x1 and x2. So those are x values. It is very important for you to understand that in a definite integral, the numbers are, and the numbers in the limit, are from the same dimension as your variable. because you can do integrals in terms of y, and in terms of z, and in terms of theta, and you guys going to learn a whole bunch of different things when you go to Calc 2. Right now, we are only dealing with integrals in x. So, your integral is x, 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 x. What it needs to be, u, 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 u. So everything has to transform to the next level. So what do? Well, we do the same old substitution. U equals 4x, du equals 4 dx, and then you can, if you want to, you can fix it by placing in 4 1/4 in front, or you can go and solve for dx. Whichever way you do, right, it will help you. But now the new component is transforming the limits, because when I write my next line, which is 1/4 integral e to the u du, this integral is no longer in x. So your limits 3 and 6 do not apply anymore. You can't use them. So what you have to do is you have to transform limits as well. So for definite integrals, we must transform limits of integration. Now that's a very straightforward procedure. You just take the numbers one by one and plug them in your substitution equation, because your substitution equation is the link between x dimension and the u dimension. So looking at the equation up there, I have for u1, which is the lower limit, I have 4 times the old x is 3, so it's 12. So now this changes to 12, and u2 is 4 times 6, which is 24. So it goes now from 12 to 24. And now you can integrate. So all of this is equal to 1/4 e to the u from 12 to 24. We have 1/4, and now you have e to the 24 minus e to the 12, and that's that. There's no plus c because it's a definite integral. So in this problem, we reinforce the fact, right? Yeah, function derivative pair and all that kind of stuff, sure, but we have limits. And again, it is very important to understand that when you have the integral, it's x, 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 x. And I can write that actually. So the integral from a to b of f of x dx. Now, as soon as you draw the situation, you realize that your a is actually just x1, the first x coordinate, and then your b, right, which encloses the area for you to calculate stuff. Your b, that's just x2. And as I said, now the new integral has to be everything u. Has to be integral of u1 to u2, and then the function in terms of u, and then du at the end. So that's what we are looking for, instead of having, I should use a different, I don't know, let's use G. So I am going to work out few examples from homework. I mean, from exercises from the textbook, and if I hit your homework question, then you just pick something else. This book is very, very interesting. Problem 43. It says integral from -1 to 2 from x squared e to the x cubed plus 1 dx. What should be my u? Remember, you're looking for functional derivative pair. If you are not embracing that concept, then you're probably not doing too hot now. So, yes, very good. You immediately locate that you have x cubed and x squared, and the x squared is the derivative of x cubed. So x cubed is a function whose derivative x squared is present. Therefore, we are going to keep the x cubed plus 1 as the sub. Du is 3x squared dx. And as you can see, I don't have 3x squared dx. In a problem, I only have x squared dx. So 3 is missing. I can fix that if it's only constant. You can't do this with variables because, you know, integral operates on variables. But constants are free to go in and out. So now I'm going to put out of nowhere 3 in front so that I can match this 100%. But now I offset the balance of the integral because this integral is supposed to be this integral, you know, you want to solve it. So you need to match these to the entire thing here. And you now know that putting in this 3 was a good idea. But you can't just put 3. You have to balance it with 1/3 in front. Because 1/3 times 3 is 1/3 times 3 is 1. I heard someone say 0 and I was like, what? Really? So, to solve this problem, now I have 1/3 integral, and instead of e to the x squared dx, I get to write du. So this is e to the u du. The entire evil integral collapsed onto just e to the u. But you're not done. You have to transform the limits. Otherwise, can't compute. So what do? You take from the top equation, you say u1, which is the bottom limit. So we are supposed to plug in -1. So we have -1 cubed plus 1. And that is 0. U2 is when we plug in 2 and we get 2 cubed plus 1, which is 9. Now these are your new limits. U1 goes on the bottom, U2 goes on top. So it's not that I only transform function into u and dx into du. I also have to change my x limits into u limits. And the link that does that is whatever your u sub equation is. So whatever you have there, That's that. Now we integrate, because now it's easy. The integral of e to the u is e to the u, so we have 1/3 e to the u from 0 to 9. You know how to compute definite integrals. So 1/3 e to the 9 minus e to the 0. E to the 0 is 1. So this is 1/3 e to the 9 minus 1. Here's one for you to try. I know how much you absolutely adore trig. So this is problem 45. Integral pi over 4 to pi over 2 cosine x over sine squared x dx. So try that one. What happened?
Do we have like a review session today or the final?
So let's finish this problem. What is our function derivative pair? Well, we have two choices. We can go with cosine x, whose derivative is negative sine x, and that's not a problem. Or we can go with sine x, whose derivative is cosine x. Now see, the trick with these guys is if you make a wrong choice, you will know. Because what you get, you will not be either, you might not be able to integrate, but also you might not be able to even put it together in a way that it makes sense. So let's just try with a wrong setup and see how badly it goes if you have a wrong choice associated for the problem. So we are going to start with u equals cosine x. And if I have u equals cosine x, then du is negative sine x dx. Do you see how in the problem dx is in the numerator and sine x is in the denominator, where in your substitution they are both in the numerator? So you can't have that. You have to have exact match. This one was supposed to be like this if you were to use it the way it's there. So when you make a wrong choice, you actually can't put these things together at all. Now let's say you want to try and force it, and you say, okay, just solve for dx and see what happens, which is du over negative sine x. I would say, okay, fine, but you will see that once you plug everything in, stuff doesn't work. For instance, integral is equal to cosine, so that's going to be u over, I don't have anything for this, so I have to copy it as is. And now instead of dx, I have du over negative sine x. Do you see that you just made it worse? It doesn't work. It doesn't work because we didn't eliminate all x's. This one survived. So it looked like a good thing to do, but it didn't work out. Because once we are done with all of our substitutions and everything, you still have x floating around. So what am I going to do instead? I'm going to try and put sine in here and see if that's going to fix the issue. And it should, because it's either u is cosine or u is sine. There is no third choice. But let's try with sine x. The derivative of that is cosine x dx. Ooh, I like that. Because I have cosine x dx in the numerator, and this is together in the numerator. So I like that. Okay, so I have integral. Cosine x dx is du. And sine x is u, so u squared. I have to transform my limits. So u1, which is the bottom limit, is sine x of pi over 4. Now that's root 2 over 2. So the bottom limit is root 2 over 2. The top limit u2 is sine of pi over 2. Well, sine of pi over 2 is 1. So the upper limit is 1. Observe that we went from sines and pi's into polynomials and numbers. So this transformation is very powerful, right? It simplified stuff a lot. It didn't just make this easy, right, in terms of, okay, now it's, it's not just it made it possible, but it made it actually very easy. So in some cases, this really simplifies life. So what do I have? I have integral from square root of 2 over 2 to 1 of u to the minus 2 du. And now I integrate, so I get u to the minus 1 over negative 1 from root 2 over 2 to 1. And now I have negative 1 over u, right, from square root of 2 to 1. And now I have to plug everything in. Now observe that for definite integrals, I am not going back to x, because I don't have to. The integral was transformed from x into u, and the limits that used to be x are now u. So when you integrate, you have a function in terms of u, and you have limits in terms of u. You just plug everything in. For definite integrals, you don't have to go back. For indefinite ones with plus c, you do, because problem is posed in x, and then your answer has to be posed in x. So I have a negative 1 over 1. That's when I plug in upper limit. Minus negative 1 over root 2 over 2. The first number is -1. Minus and minus gives me plus, and this becomes square root of 2 over 2 when you flip it because it was in denominator. You have to rationalize because we are allergic at irrational denominators. And we have -1 plus 2 root 2 over 2. Well, now these guys cancel, and the whole thing is just root 2 minus 1. About 0.42. So that will be the answer. And as you can see, your answer is a number now. You can get the calculator and calculate exactly what this is. But that's that. We have time for one more. What do you mean? Class ends at 8:30. You didn't know that? It's a late start class. Yeah, look it up on the.
I know.
Oh, you do?
When's the review though? You didn't answer that.
Yeah, exactly. Because we're doing the problems. You're not paying attention for the regular problems, and then you want extra stuff. Relax. So one more problem. The integral of 0 to ln 4 of e to the x divided by 2 plus 2e to the x dx. So this would probably be what is the spiciest problem tonight. So you're looking at this, and I'll tell you one of the secrets. It's not always 100%, but most of the time, if you have a rational situation, something divided by something, denominator should be u. Because you can never have du in the denominator. So the function should be in the denominator, and its derivative, which produces du, should be then on top. So that helps with us making the choice that u should be 2 plus 2e to the x. And the derivative of that du is 2e to the x dx. Now, we're happy that we at least have e to the x dx. I need that too. So I'll fix it. I put 2 in, and I put 1/2 in front to fix the issue for substitution. So now I have 1/2 integral. 2e to the x dx becomes du, and the entire denominator is u. Now I have to transform my limits. So u1 is the one on the bottom, and I will be plugging in 0 in the u formula. So that's 2 plus 2e to the 0. E to the 0 is 1, so the whole thing is 4. And the u2 is 2 plus 2e to the ln 4. Now e and ln will cancel. 2 times 4 is 8 plus 2 is 10. So the top limit is 10. So now, does anyone know what's the limit of du over u? It was there on the exam. What's the integral of du over u? Yes, natural log. Very good. So the answer over here is 1/2 ln absolute u from 4 to 10. This is 1/2 ln 10 minus ln 4. Now, if you know your rules for logs, you know that subtraction of 2 logs goes into division of arguments. So it's 1/2 ln of 10 over 4, which is actually 1/2 ln of 5/2. Now you can go and take this 1/2 and make a square root if you want to, but that will not help compute anything because you can't take square root of 5/2 without a calculator. And this takes care of the whole thing. Guys, that's Calc 1. I know, right? Done. Done and done. I'll see you around in life.